Hello Math 122, welcome to the last video for our class together. So in this video we're going to be covering section 6.6, which is all about integration by substitution. So we'll start off by recalling that back in the section where you learned how to differentiate, there was a rule called the chain rule, and this chain rule allowed you to differentiate a function that could be written as the composition of two other functions. So let's remember that rule. If I have a function f of g of x and I want to take the derivative, then we said this is equal to f prime of g of x times g prime of x, or put in another way, the derivative of the outer function of the inner function times the derivative of the inner function. But we can also go in the opposite direction as well. So say that we start with the function f prime of g of x times g prime of x. Well, this equation for the chain rule here tells us that the integral of f prime of g of x times g prime of x is going to be equal to the composition of f and g. So f of g of x plus some constant of integration c. So if we can take the integrand inside of some indefinite or definite integral and write it in the form f prime of g of x times g prime of x, then we can find the antiderivative because it's just going to be f of g of x. So ultimately, this observation leads to a method of integration that's called u-substitution, and this is the last integration tool that you're going to learn in this class. So let's start off with some examples. So in these examples, we're going to use the chain rule to find the derivative of a function f of x, and then write the corresponding anti-differentiation formula after we have the derivative. So in the first example, f of x is equal to e to the x squared. So first we're going to take the derivative, and this is going to be equal to e to the x squared, but chain rule tells us we have to multiply by the derivative of the inner function, which in this case is x squared, and we end up with 2x times e to the x squared. So this is a type of problem that you could have done back in chapter 3, but now that we have antiderivatives, this tells us we can go the opposite direction. So if I start with the function 2x times e to the x squared dx, the antiderivative of that function will be e to the x squared plus c. So here we're starting with the derivative and going in the other direction. With the tools that we have so far, if I gave you an integration problem with this function as the integrand, you probably wouldn't be able to figure out what the antiderivative is without a lot of thought. But eventually, as we develop u-substitution, we're going to be able to do integrals like this without too much trouble. All right, so for the next example, f of x is equal to 1/6 times x squared plus 1 to the 6th power. So again, we take the derivative. 1/6 is just a constant, so I can pull it out. And I have a 6 times x squared plus 1 to the 5th power. And now I'm going to multiply by the derivative of the inner function x squared plus 1. And now I'll rewrite this, and we get an x squared plus 1 to the 5th power times the derivative of x squared plus 1, which is just 2x. So again, this tells us that if I started with the derivative, so if I started with 2x times x squared plus 1 to the 5th power, and I needed to find an antiderivative, well, the antiderivative would then be 1/6 times x squared plus 1 to the 6th power plus a constant of integration. So these examples are showing this relationship back and forth between taking the derivative using the chain rule and then looking at the corresponding antiderivative. And again, u-substitution is going to give us the ability to take an integrand and view it as the form f prime of g of x times g prime of x, and then write out the antiderivative as f of g of x. Alright, now let's look at this new method of integration called u-substitution. And instead of trying to explain everything before I do an example, I think I'm just going to do a bunch of different examples and give my explanations as we go, and hopefully you can kind of pick up on the general methodology that we use here. Alright, so in this first example, we want to use the method of u-substitution to calculate the indefinite integral of 1 over x squared plus 4 times 2x dx. So if you're going to use u-substitution, the first thing that you want to do is look for some smaller function within the integrand that's derivative shows up inside of the integrand as well. So in this case, I notice that I have an x squared plus 4 sitting inside of the integrand in the denominator here. And I notice that the derivative of x squared plus 4 is equal to 2x. And 2x is also showing up inside of the integral here. So I'll write that down. Notice that 2x also appears in the integrand. So once you have this occurrence, you have a smaller function in the integrand such that its derivative also shows up in the integrand. You're going to let the variable u equal that smaller function that you found from step 1. So in this case, we're going to take u and we're going to set it equal to x squared plus 4. The third step, we're going to take that u and we're going to differentiate it with respect to x and then solve for du. So here, since u is equal to x squared plus 4, the derivative of u with respect to x is equal to 2x. And from here, I can multiply both sides by dx and get du is equal to 2x dx. So that's the end of this step. And now we want to use the u that we defined and du to substitute back into the integral. So here we started with the integral of 1 over x squared plus 4 times 2x dx. But we said that u is equal to x squared plus 4. So substituting with u, we get a 1 over u now. And now du is equal to this 2x dx. So we rewrite it as the integral of 1 over u du. Now the next step is to find the antiderivative of this new integral in terms of u. So here, the integral of 1 over u du is an integral that we already know. So this is equal to the natural log of the absolute value of u plus some constant of integration c. And then finally, we're going to substitute the smaller function in terms of x back in for u in this new antiderivative that we found. So we have the integral of 1 over x squared plus 4 times 2x dx was equal to the integral of 1 over u du, which is equal to the natural log of the absolute value of u plus c. And now we substitute back in for u, and we get the natural log of x squared plus 4 plus c. So this would be our final antiderivative. Okay, let's do another example with u substitution. So here we want to find the indefinite integral of t times e to the t squared plus 1 dt. So again, I start off by trying to find a smaller function inside of this integrand whose derivative also shows up inside of the integrand. So notice that if I take the derivative of the t squared plus 1 that's showing up as the exponent of e, I get a 2t. And 2t is almost t, which is another part of the integrand here. So it's not quite t, but 2t is pretty close. It's a constant multiple of t. So even though we don't get a 2t inside of there, we're still going to let u equal t squared plus 1 because 2t is a constant multiple of that t that's showing up. So we're going to let u equal t squared plus 1. And if we do this, then we have that du dt is equal to 2t. And solving for du, we get du is equal to 2t dt. But if I want to do this substitution with u, I don't want to substitute du in for 2t dt because I don't have a 2t times dt inside of my integral. I only have a t times dt inside of my integral. So I'm going to divide both sides of this equation here by 2, and I get a 1/2 du is equal to t times dt. And now I'm ready to do the substitution. So from here, this integral t of e to the t squared plus 1 dt is equal to the integral of e to the t squared plus 1 times t dt. So I'm taking the t on the left-hand side and the dt, and I'm just putting them together, so the substitution is easier. And now t squared plus 1 was equal to u, so I have e to the u, and now t dt we found was equal to 1/2 du. So I get a 1/2 du here. And now I can take that 1/2 and pull it out of the integral. So I just have 1/2 times the integral of e to the u du. And I know the integral of e to the u. So I get a 1/2 times e to the u plus c. And then finally, take our expression for u in terms of x and substitute it back in. And I get a 1/2 times e to the t squared plus 1 plus c. So this would be our antiderivative. All right, let's do another example of u-substitution. So at this point, you might be asking yourself, how do I know what to make u when I look at the integrand? And the honest answer is you're only going to figure it out by doing many different problems. So you need lots of practice so that you can recognize different patterns that are appearing. But I can tell you in this case, I look inside of the integral and I notice that I have an x to the 4th power that's showing up and I have an x to the 3rd power that's showing up. And I know when I have x to some power and I take the derivative, it decreases the power by 1. So I'm already thinking when I look at this integral, I'm probably going to end up making u something like x to the 4, or maybe x to the 4 plus 5. So in this case, I notice that the derivative of x to the 4 plus 5 is going to be equal to 4 times x cubed. And again, this 4 times x cubed is not quite the x cubed that's showing up in here, but it's a constant multiple of x cubed. And that constant multiple is going to be good enough. Okay, so let's let u equal this x to the 4 plus 5, and then see what happens. So if we do that, when we find the derivative of u with respect to x, we're going to get a 4x cubed. And now we can solve for du, and this will give us a 4x cubed dx. But I don't want to substitute du in for 4x cubed dx because I don't have a 4x cubed sitting inside of the integral. I only have 1x cubed. So I'm going to divide both sides of this equation by 4 and get a 1/4 du is equal to x cubed dx. And now I'm ready to substitute that in for x cubed dx. So let's do the substitution. So I have my integral of x cubed times x to the 4 plus 5 dx, and now let's substitute. So this square root of x to the 4 plus 5 is going to become the square root of u, and then the x cubed times dx is going to give me a 1/4 du. And now the 1/4 can be pulled out of this integral, and the square root of u will become a u to the 1/2. So now I have 1/4 times the integral of u to the 1/2 du. And now I can solve this integral in terms of u. So 1/4, and now u to the 1/2, this is going to give me a 2/3 times u to the 3/2 using the power rule, the rule that we have for x to the n, plus our constant of integration. Now simplifying a little bit, I get a 1/6 times u to the 3/2 plus c. And then finally, we're going to take that expression we had for u in terms of x and substitute it back in. And we get 1/6 times x to the 4 plus 5, all to the 3/2 plus c. So this is our antiderivative in terms of x. All right, let's do another example with u-substitution, a little bit of a different pattern that's showing up inside of this integral here. So this time, again, I'm looking for that function inside of my integrand that has a derivative that also shows up inside of there. So I notice that if I look at the natural log of x and I take the derivative, I'm going to get a 1/x. And I notice that I have this x in the denominator, which means that I have a 1/x sitting inside of my integral. So we're going to let u equal the natural log of x, and then we're going to see what happens, and hopefully things work out well. So we have the derivative of u with respect to x is going to be 1 over x, and now solving for du, we get du is equal to 1 over x dx, and now we do the substitution. So the integral of the square root of the natural log of x over x dx, this is equal to the integral of the square root of the natural log of x times 1 over x dx. But now the substitution is clear from here. So I have the integral, and since u is equal to the natural log of x, I get a square root of u, and now du is equal to 1 over x dx. So I get the square root of u du. I can rewrite this as u to the 1/2 du. And now I can take the integral with respect to u, and I get a 2/3 times u to the 3/2 plus c, and then finally substitute back in for u in terms of x. We get 2/3 times the natural log of x to the 3/2 plus c. So this will be our antiderivative in terms of x. So hopefully you're starting to catch on to the pattern of u-substitution that we've been using to solve these different indefinite integrals. But we also talked about definite integrals, and now we're going to move on to using u-substitution for definite integrals as well. So for definite integrals, there are two slightly different methods that we can use to solve definite integrals with u-substitution. So I'm going to take you through both methods, and you do need to know both of them, but they're only slightly different, and it shouldn't be too difficult for you to remember both. So the first one, I'm just going to call the back substitution method, because it's the method that allows us to take the integral with respect to u and then substitute our expression in x back in for u and then solve the definite integral. The other one is going to have a different name, but we'll get there in a little bit. So in this example, we want to compute the definite integral from 0 to 2 of x times e to the x squared dx. And we're going to use this first method called back substitution. So the first thing that we're going to do is use u-substitution to find an antiderivative of x times e to the x squared. So I notice that inside of the integral here, the derivative of x squared is going to be equal to 2x, and 2x is a constant multiple of x, which also shows up inside of the integral here. So we're going to let u be equal to x squared, so that if I take the derivative of u with respect to x, I get a 2x, and now solving for du, I get du is equal to 2x times dx. And then from here, again, I don't have a 2x dx inside of my integral, I only have a 1x dx. So I want to make sure that I have just x dx by itself on the right-hand side. So I'm going to divide by a 2 and get 1/2 du is equal to x times dx. And now we're ready for the substitution. So instead of looking at the definite integral, we're just trying to find an antiderivative for x times e to the x squared. So we're going to take the indefinite integral of x times e to the x squared dx. And now we can rewrite that in terms of u, and we get e to the u times 1/2 du, and this is going to be equal to 1/2 times the integral of e to the u du, and now I can take that indefinite integral, this is just a 1/2 times e to the u plus c, and then finally I can back substitute that x expression in for u here. So we get 1/2 times e to the x squared plus c. So this is an antiderivative in terms of x for x times e to the x squared. And now I'm going to take that antiderivative that I found and use it with the fundamental theorem of calculus to evaluate the definite integral. So we have this definite integral from 0 to 2 of x times e to the x squared dx is equal to, and I just found an antiderivative in part 1, so this is going to be equal to our antiderivative 1/2 times e to the x squared evaluated at 2 and 0. So that gives me a 1/2 times e to the 2 squared minus 1/2 times e to the 0. And this is equal to 1/2 times e to the 4 minus 1/2. And now factoring out the 1/2, we get 1/2 times e to the 4 minus 1. So this is the value of this definite integral here, using the back substitution method, where we first find an antiderivative for the integrand in terms of x, and then use that antiderivative with the fundamental theorem of calculus to evaluate the definite integral. Now let's do the same example using the second method for u-substitution and definite integrals. So this second method, we're going to change the limits of integration while we're calculating. And in this method, there's no back substitution. So we're going to take those limits of integration from the original integral, in this case 0 and 2, and we're going to change them to respect our new variable u, and then we're never going to end up back substituting our expression in x back in for u. All right, so we start off by finding an appropriate u substitution for the integrand. So this is really the same thing that we did in the first method. Not much has changed. So notice that if I take the derivative of this x squared expression showing up as a power of e, I get 2x. And this is a constant multiple of the x that's showing up inside of there. So we're going to let u equal to x squared. And once we do that, then we get that the derivative of u is equal to 2x, which implies that du is equal to 2x dx. And then we have 1/2 times du is equal to x dx. And from here, we're ready to substitute in for the integrand. But if we're going to substitute in for the integrand in terms of u, we first need to take the limits of integration, x equals 0 and x equals 2, and we're going to change them to the corresponding limits of integration in the variable u. So let me show you how to do that. In this case, the limits of integration are x equals 0 and x equals 2. But since we let u equal x squared, then when x is equal to 0, u is going to be equal to 0 squared, which is just 0. And when x is equal to 2, u is going to be equal to 2 squared, which is 4. So now we can substitute, but we need to take those limits of integration, x equals 0 and x equals 2, and change them to u equals 0 and u equals 4. So now we're going to have the definite integral from 0 to 2 of x times e to the x squared dx is equal to, and now we substitute for our limits of integration in terms of u, so we get a 0 at the bottom and a 4 at the top. And now substitute in terms of u. So again, we get e to the u times 1/2 du. And now we take the 1/2 and pull it out of this integral. So we have 1/2 times the definite integral from 0 to 4 of e to the u du. And then finally, instead of ever substituting back in terms of x, we're just going to evaluate this new definite integral in terms of u. So we have 1/2 times the integral from 0 to 4 of e to the u du is equal to 1/2, and an antiderivative of e to the u is just e to the u, and we're evaluating from 0 to 4 in this case. So we get 1/2 times e to the 4 minus e to the 0, which is equal to 1/2 times e to the 4 minus 1. So in this case, we never substituted back in for x with our expression in u. And notice that our answer we got, 1/2 times e to the 4 minus 1, is the same as the answer we got from the first method, 1/2 times e to the 4 minus 1. Okay, and finally, in our last example, let's use both methods again to evaluate the definite integral from 0 to 2 of x over 5 plus x squared squared dx. So let's start off with method 1, the method that uses back substitution. All right, so notice that I have a 5 plus x squared inside of there, and if I take the derivative of 5 plus x squared, I get 2x. which is a constant multiple of this x showing up here. So let's say that again, the derivative of 5 plus x squared is equal to 2x. So we're going to let u be equal to 5 plus x squared, so that if I take the derivative of u with respect to x, I get a 2x, which implies that du is equal to 2x dx. But now I want just x dx on the right-hand side for substitution, so I get 1/2 du is equal to x dx. Okay, and since we're using this back substitution method, I'm just worried about finding an antiderivative for the integrand here. So we're going to look at the indefinite integral of x over 5 plus x squared dx, and now substitute in with our u. So we end up with a 1 over u squared times 1/2 du. And I can make this look a little bit better. So we can take the 1/2 out of the integral and just get a 1/2 times the integral of 1 over u squared du. And now rewrite that as 1/2 times the integral of u to the negative 2 du. And now I know how to integrate u to the negative 2. So I'm going to get a 1/2 and now use the rule that we have for some variable to some power when we integrate. This is going to give me a negative u to the minus 1 plus c. And rewriting this, I get minus 1 over 2 times u plus c. And then finally, substitute back in for u in terms of x. And I get a minus 1 over 2 times 5 plus x squared plus c. So this is going to be our antiderivative for the integrand that we started with. And now we're going to use the fundamental theorem of calculus along with this antiderivative that we just found. So we have that the definite integral from 0 to 2 of x over 5 plus x squared dx is equal to this antiderivative minus 1 over 2 times 5 plus x squared, evaluated from 0 to 2. And this will give us a minus 1 over 2 times 5 plus 4 plus a 1 over 2 times 5 plus 0. And this is just a minus 1 over 18 plus a 1 over 10. And if you would plug this into your calculator or do a little bit of math, this ends up being 2 over 45. So the answer to this definite integral is 2 over 45. Okay, so let's use the second method as well. Again, we start off by noticing that the derivative of 5 plus x squared is equal to 2x. So this is exactly how we started the first method. And so we're going to let u equal 5 plus x squared again, so that du dx is equal to 2x, which implies that du is equal to 2x dx, which implies that 1/2 du is equal to x dx. And we're almost ready to do the substitution, but this time we're not finding an antiderivative. We're going to take the limits of integration from that original integral and we're going to change them so that they make sense in terms of u. And then we're just going to do the rest of the problem in terms of u without ever substituting back in for x. Okay, so our limits of integration were x equals 0 and x equals 2. Let's see what happens to x equals 0. So the limit of integration, x equals 0, is going to go to u equals 5 plus 0 squared, which is just equal to 5. So because u is equal to 5 plus x squared, and because x is equal to 0, the new limit of integration in terms of u is going to be 5 plus 0 squared, which is just 5. And the limit of integration, x equals 2, is going to go to u equals 5 plus 2 squared, which is just 9. And now we can take our original definite integral and rewrite it. So we started with the integral from 0 to 2 of x over 5 plus x squared squared dx. But now this is going to be equal to the integral from 5 to 9, and now we can do our substitution. So we have 1 over u squared times 1/2 du. Now we can take the 1/2 and pull it out of the integral. We get 1/2 times the integral from 5 to 9, 1 over u squared du. And I'm just going to rewrite this as u to the minus 2 du. All right, and now let's look for an antiderivative. I have 1/2 times minus u to the minus 1 evaluated from 5 to 9. And this is going to give me a minus 1 over 2u evaluated from 5 to 9. And now I can plug in, and I end up with something that looks very familiar. So I have a minus 1 over 18 plus a 1 over 10. And again, if you simplify this, you end up with 2 over 45. So in this second method, we never substitute back in terms of x. We just change the limits of integration from x equals 0 to x equals 2 to u equals 5 to u equals 9. And then we do the entire rest of the problem in terms of u instead. But either of these methods works perfectly fine. But there will be different questions that are going to force you to know how to do either one. So I'll test you on both of them. And it's important to note here, it's possible that as you're doing the homework, you're going to get somewhat frustrated because you haven't seen something like this before. And you're going to wonder, how am I supposed to know what I should make u in all of these different scenarios? Ultimately, the only way that you can know what to make u is by doing a bunch of different practice problems. There's really no shortcut to it. And you just have to see patterns that show up over and over again. So make sure that you're doing all of the homework here, all of the practice problems you possibly can. And if you need any help with any of those problems, just send me an email. On this homework, I'm not going to have any limit to how many attempts you can have for each question. You can attempt them as many times as you want. But ultimately, these questions are going to cause you to struggle a little bit until you really get this method down. And in the meantime, you should be going to my office hours or sending me emails or going to SI sessions to get help if you need to do it and you haven't seen this before. But I wish you the best of luck in your homework. And again, just let me know if you have any problems.